Hello everyone, I'm Dr. Somicham. Today, we're diving into one of the most helpful yet underappreciated tools in descriptive statistics, the stem and leaf plot or Stemplots. It's a way of turning raw numbers into a visual format that can help us actually see patterns in our data. Let's start with this idea. When you're handed a long list of numbers, whether it's test scores, food sizes, or miles per gallon, it's easy to feel overwhelmed. But when you organize those numbers visually, we often start to see meaningful trends emerge. You've probably encountered charts like bar graphs or pie charts. Those are good tools. But stem and leaf plots give us something a little different. They allow us to view the individual values in our data set while also capturing the overall shape of the data. Let's walk through an original example. Imagine a public school district has just completed vision screening tests for 30 sixth graders. The data collected are the scores from a standard visual acuity test measured in decimal form like 1.0 for 20/20 vision. These scores range from 0.6 to 1.4. Now, looking at 30 numbers on a spreadsheet doesn't tell us much. But let's organize the scores into a stem plot. We separate each score into a stem, the whole number, and a leaf, the decimal. So 1.2 becomes stem equals 1, and leaf equals 2. We'll list the stems down the side in order and align the leaves horizontally. Once we do this, we start seeing that most students scored between 1.0 and 1.2, with a few students below 0.8 and a few above 1.3. That pattern was invisible when we just looked at the raw scores. You can immediately spot where the data cluster, the range of values, and any outliers, like a single student with a score of 0.6. Let's pause here and talk about outliers. An outlier is a value that sits far outside the typical range of your data. It could mean a measurement error, or it could reflect a meaningful exception. In our case, the 0.6 might indicate a vision issue that requires follow-up. We wouldn't know that just from the list of scores, but the stem plot draws our attention to it immediately. Now, let's try a very different data set. Suppose a local farmer's market has been tracking the weight of apples sold in one weekend in ounces. They record 40 apple weights ranging from 4.2 ounces to 9.9 ounces. Again, we turn to a stem and leaf plot. The stem would be the whole number like 4, 5, 6, etc. And the leaf would be the 10th digit. So an apple weighing 6.5 ounces would be stem equals 6, leaf equals 5. When we organize this into a stem plot, we might notice a peak in the 6.0 to 7.0 range, with a few unusually large apples near 9.5 ounces. Even better, we can calculate the midpoint. If we have 40 apple weights, we find the 20th and 21st values, average them, and locate the median. We can also observe whether the distribution is symmetrical or skewed. Do we see a long tail on one side? That tells us something about the consistency of apple sizes that weekend. So, why do we use stem plots? They allow us to preserve the original data values, show the shape of the distribution, help identify clusters, gaps, and outliers, and are ideal for small to moderate-sized data sets. But there's more. Suppose we're comparing two data sets, say the number of minutes people spend on social media per day in two different age groups, 18 to 29-year-olds and 50 to 64-year-olds. If we construct a back-to-back stem plot, we can place one group's leaves on the left and the other on the right. This lets us visually compare usage patterns. We might see that the younger group clusters around 120 minutes per day, while the older group tends to hover around 45. Again, this kind of insight is hard to extract from spreadsheets alone. Let me also show you how we can adjust the resolution of a stem plot. If your data is too compressed, say many values are grouped on a single stem, you can split each stem into two. One line for leaves ending in 0 to 4, and another for 5 to 9. This helps you zoom in on your data structure without losing the overall picture. Now, a quick note. Stem and leaf plots are not great for very large data sets. Imagine trying to build one for thousands of people. It would become overwhelming and hard to read. In those cases, we shift to tools like histograms or box plots. But for a classroom, a clinic, a school district, a department of a university, or a small business, stem plots are a powerful way to begin understanding what your data is telling you. Another example involves a retail store tracking the number of items sold per day over a month. Suppose they have data for 30 days, with sales ranging from 15 to 75 items per day. By creating a stem plot, the store can visualize the distribution of daily sales. The stem would be the tens digit, and the leaf would be the units digit. For instance, a day with 42 items sold would be stem equals 4 and leaf equals 2. When we organize this data into a stem plot, we might see that most days have sales between 30 and 50 items, with a few days exceeding 70 items. This visualization helps the store understand their sales patterns and identify peak sales days. In these examples, the stem plot provides a clear visual representation of the data, making it easier to identify trends, clusters, and outliers. This tool is invaluable for anyone looking to make sense of their data and draw meaningful conclusions. A stem plot is not just a visual, it's a conversation starter. It helps you ask, what's typical? What's unusual? What do I need to look into further? Now, I encourage you to try making a stem plot with your own small data set. Maybe from your work, your research, or even your daily habits. You might be surprised at what you learn.